Hello, I'm Gianluca Tabella, a PhD candidate at the Department of Electronic Systems of the Norwegian University of Science and Technology, NTNU. This work, data fusion for subsea oil spill detection through wireless sensor networks, has been carried out together with Professor Pierluigi Salvo Rossi from the same department, Professor Nicola Paltrinieri from the Department of Mechanical and Industrial Engineering of the same university, and Professor Valerio Cozzani from the Department of Civil, Chemical, Environmental and Materials Engineering from the University of Bologna. The reason why this work is important is because of the increasing need for digitalization of the oil and gas industry. Therefore, we propose a new method for oil spill detection that takes advantage of a wireless sensor network as a leak detection system. The idea is to move from a static view of the risk assessment to a dynamic view of the risk assessment, so that the risk estimation becomes time-dependent, allowing real-time estimation, and data-dependent, so that we can take advantage of the information sent by the sensors. As we can see, the data acquisition and the data processing can be used as a tool for the decision-making on offshore platforms. Nowadays, leak detection systems for subsea production system monitoring are classified into two main categories. Internal leak detection systems, where the sensors measure process variables like the pressure or the flow rate, and external leak detection systems, where sensors sense the external environment. And in this work, we want to focus on the use of passive acoustic sensors to be used in a wireless sensor network as a leak detection system. So the first step is the decision of what kind of wireless sensor network topology we want to employ. Let's remember that subsea conditions impose low energy consumption. So for this reason, we want to use local binary decisions. So it means that if a sensor senses the presence of a spill, it will send this information to the fusion center, which will declare, which will take a more reliable and global decision on whether there is a spill or not, based on all the communications received by the sensors belonging to the network. This has two advantages. The first is low processing cost, and the second is low communication cost. Of course, on the other hand, we will have some extent of loss of information. The next step is to analyze the underwater acoustic signal. So we can see that the Kate sensor will sense the sound pressure, and we have two different situations. The first is the null hypothesis, H0, in which the sensor will only sense noise. The alternative hypothesis, H1, is the hypothesis in which there is a leak, and the sensor will sense noise plus the contribution of the leak multiplied by the amplitude attenuation function, which depends on the position of the sensor and the position of the leak. So we can see from the picture that we have a Gaussian model for both hypotheses. More specifically, the amplitude attenuation function depends on the distance between the sensor and the leak. And in order to model this, we had to combine two different contributions. The first is the seawater absorption, and it was modeled by using the Francois and Garrison equation with the help of the updated UNESCO equation for the calculation of the speed of sound, and then the geometrical spreading. So the equation that we can see below is the equation that represents actually the model used for the amplitude attenuation function. Now we have to understand how the sensor will perform the local detection. So considering the statistic of the signal, the optimal test is the energy test, in which every single sensor will perform a test on the energy of the signal and will compare it to a threshold. So since the statistic of the signal is known, we can calculate the probability of detection and the probability of false alarm. Unfortunately, the probability of detection depends on the leak position. So for this reason, it cannot be calculated directly. So what we propose is to localize all the hotspots present in the system. What are the hotspots? They are those components of the subsea production system whose failure would cause a spill. So we can calculate average local performances by averaging all the values of probability of detection, assuming all the time that a different hotspot is the leak. Now we want to see how the fusion center will perform the global detection. So we compare two different fusion rules. The first is the counting rule, in which the fusion center counts the number of sensors detecting a spill and will compare it with a threshold. The other one is a modified version of the Chair-Varshney Rule, in which we used the average performances that we calculated before doing the hotspot localization. And also in this case, the number will be compared to a threshold. Also in this case, we can do the same kind of reasoning as before, and we can say that the global performances, so the global probability of detection and false alarm, can be calculated, but also in this case, they are leak dependent. So they depend on the position of the leak. So doing the same kind of procedure as before, so by localizing the hotspot of the system, we can calculate the average global performances. As a last step, we need to select an appropriate threshold for the sensors and the fusion center. This is done by optimization of an objective function, and in this case, we chose the Uden index, which represents the difference between the probability of detection and the probability of false alarm, as it can be seen in the picture. The first step is to obtain the local threshold for each sensor. Once we do this, the same thing can be done to obtain the global threshold in step 2. In both cases, we want to use the average performances with respect to the hotspots of the subsea production system. It is important to perform the steps in order, since the global performances depend on the local thresholds. This methodology has been applied to a case study, the Goliat FPSO, which is a production platform located in the Norwegian Barents Sea, where 3 hydrophones are used to monitor the manifold of each template. So after a reliability analysis on the manifold of the template, we found 20 hotspots in the system. So once applying the methodology shown before to the case study, we can see the ROC curves of the counting rule and the modified Chair-Varshney rule at the fusion center in 2 different cases with different signal-to-noise ratio. So we can see that the counting rule has only k+2 number of thresholds in the curve, where k is the number of sensors, while the modified Chair-Varshney rule has 2 to the power of k+1 number of thresholds, in this case 9. So there is an increase of number of possible thresholds that the system can use. So since we want to optimize the Uden index, we see that in this case, the best values of Uden index are obtained if we use the modified Chair-Varshney rule. To conclude, we can say that the modified Chair-Varshney rule shows better results than the counting rule, since it shows the highest value of Uden index. Also, the availability of more thresholds makes the modified Chair-Varshney rule more flexible than the counting rule. This work shows an integration of sensor fusion techniques with reliability data of the subsea production system, representing a step forward for the digitalization of the oil and gas industry. Future work consists of the localization of the leak, quickest change detection, and improved techniques for threshold optimization. Thanks for your attention, and if you have any question after the video, I will be very happy to give you an answer.